Good day, and welcome to our webcast, Case Studies in AI-Based Predictive Maintenance and Quality, brought to you by CFE Media and Technology and sponsored by Epicor, Oracle NetSuite, and Wago. I'm Kevin Parker, an editor with CFE Media and Plant Engineering Magazine. Joining us today will be Dr. David Siegel of Predictronics Corporation and Mo Abu Ali of lloT. Stay tuned for what's sure to be an interesting webinar and presentation. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. A certificate of completion will be available for each participant to download upon successful completion of a test at the end of the presentations. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. To take the Learning Unit exam, use the Learning Unit Exam tab option at the top of your screen. The exam will open in a separate browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. Here are some tips to help you get the most from today's webcast. If you're experiencing issues with your slides or audio, refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of this webcast by adjusting the volume on your computer or by adjusting it on the webcast platform. If you are having technical problems with audio or the slide presentation, click on the question mark at the top right-hand corner of your screen to access a list of system checks to try before contacting an online technician. If you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. Type your questions for our speakers in the Ask a Question box as well. The live Q&A session will begin after the presentations conclude. Today's webcast is being recorded. You will receive an email within a week with a link to the on-demand event. To download the certificate of completion, a PDF copy of the presentation, and other additional resources, use the Event Resources tab on the left-hand side of the screen. These documents will also be available with the on-demand version of the webcast. This webcast is being recorded, including the Q&A session. We'll send you an email message within a week with a direct link to the archive. The exam will be posted on CFE Media websites with the on-demand version. The exam is for one RECEP ASEC Certified Professional Development Hour. Before beginning the presentation, we invite you to view the following short videos provided by today's sponsors, Epicor, Oracle NetSuite, and Wago. At the conclusion of the videos, you may experience a few seconds of silence to compensate for varied internet speeds. Please stay tuned.
If you don't know your numbers, you don't know your business. I learned this the hard way with my first company, so I created NetSuite, the world's #1 cloud business system. NetSuite gives you the visibility and control you need to make smart decisions and grow with confidence. That's why companies who use NetSuite grow 3 times faster than the S&P 500.
Schedule your free product tour right now at netsuite.com/grow.
The Wago PFC with cloud connectivity is easy to configure for your next IoT application. Compatible with all the big players like Amazon Web Services, Microsoft Azure, IBM's Bluemix, or your own hosted MQTT platform. The configuration is done using the controller's web-based management. Simply choose your cloud and type in your account's IoT endpoint details and you're all set. TLS encryption is supported on all platforms. With that entered, you can monitor the network status to verify your controller indeed connects. If you do lose connection, the controller has built-in buffering either to internal flash or an SD card up to 32 gigabytes, just by selecting the cache mode here. The controller is now ready to publish and subscribe your data using the easy-to-use eCockpit library function blocks. If you'd like more information on this feature, please see the Wago application note in the link below.
Manufacturers are facing a barrage of information about how new disruptive technologies will change the face of their industry. But for manufacturers to embrace mobile, social, analytics, cloud, and Industry 4.0, they must have a clear understanding of the technology value add within the context of today's business environment. With all this talk about Industry 4.0 and data deluge from all the interconnected devices on the factory floor and analysis in the back office, manufacturers may wonder, where does ERP fit into this new digital frontier? The reality is that ERP is more relevant in this equation than ever before, and manufacturers need the ability to contextualize data and integrate it into downstream process flows. To do this, ERP systems must be reimagined to meet the needs of new and emerging manufacturing technologies. Responsiveness demands simplicity and mobility, with tools designed to meet the specific needs of specific users. With an ERP system that delivers this, manufacturers can check off a big box on their Industry 4.0 readiness checklist and make good on the promise of real-time, actionable intelligence.
Welcome back. I'd now like to introduce today's speakers, Dr. David Siegel and Mo Abu-Ali. Dr. David Siegel is the Chief Technology Officer for Predictronics. His current role includes developing the company's technology roadmap, as well as leading the implementation team for predictive monitoring and machine learning-based solutions. Prior to joining Predictronics, Dr. Siegel was a research assistant at the Center for Intelligent Maintenance Systems at the University of Cincinnati. Siegel has written or co-written more than 40 papers in the area of condition-based monitoring, intelligent maintenance, and machine learning solutions for improved diagnostics and prognostics. Mo Abu-Ali is a managing partner and chief evangelist with lloT LLC, located in the Cincinnati area. lloT helps clients create a competitive advantage through digital transformation. In addition, Mo is adjunct professor at the University of Cincinnati College of Engineering and Applied Science. Mo has a doctorate in the philosophy of industrial engineering from the University of Cincinnati. Mo, welcome back to our IIoT webinar series, and please go ahead.
Yeah, thank you very much, Kevin, for the opportunity to speak again, and I appreciate speaking today with my good friend, Dr. David Siegel from our Predictronics team. The topic of our presentation today is digital transformation powered by the industrial IoT and predictive analytics, and we will focus on very practical case studies in applying artificial intelligence for two use cases. One focusing around predictive maintenance and the other focusing around predictive quality. As Kevin said, I've been in the industry for over 20 years, and I've had the pleasure of working at companies like Toyota, Omron, P&G, and a lot of these projects I actually conducted with Dr. David Siegel and our industrial data science team. So we're going to go through 3 points, and I'd like to cover the first and then hand it to Dr. Siegel to go over the use cases. I would like to set the stage for industrial IoT, Industry 4.0, and the business case behind these solutions. So kind of starting from the top. So let's get started. So obviously, in the field today, there's a lot of terminology, right? You might have heard the terms Internet of Things, IoT, Industrial Internet of Things, IIoT, Industry 4.0, digital transformation, right? Manufacturing 4.0. So I want to make a definition of what these terms mean to us, and I'd like to set the stage for this terminology and this presentation. So let's start from the top, right? The field of Internet of Things, or IoT, is not a new field by any means, right? This field has been around for many years, maybe under different namings. But in safety-critical industries, especially in energy, nuclear power plants, aviation industry, where there is a need to collect data and monitor safety-critical equipment, right? Things have been connected and data has been collected for these types of assets and applications for several decades. But there comes applying these ideas and philosophies and methodologies within manufacturing, right? And there comes the field of industrial IoT, which is the application of IoT in the industrial space. And when we look at a manufacturing plant, any plant, you will see several layers within this manufacturing facility, which we refer to sometimes as a digital stack, right? You have your machine layer, you have your CNCs, your PLCs, your sensors, you have your SCADA layer, which is your supervisory control and data acquisition. Some companies are using solutions to use OPC, for example, to collect data from equipment today and sensors. Some manufacturing plants are using manufacturing execution systems, MES, and those MES solutions are tying the plant floor layer to the business layer, which is your enterprise resource planning, right? It is a fact, however, that in many cases, those layers are fragmented or they may not be connected to each other, right? And it's very important for us to usually define what is the digital maturity of the manufacturing plant. And by assessing this baseline maturity level, we're able to then collect data and create a strategy around digital transforming of this manufacturing facility. So now that we understand IIoT and the different stacks that make it, there comes initiatives that are used to drive IoT adoption today. And one of those initiatives is Industry 4.0 or the Fourth Industrial Revolution. This initiative was actually born in Germany initially many years ago. And the idea here is tying the IT layer with the OT layer, okay? Information technology marries with operational technology. And this means using IT systems to connect, to collect data, and to apply analytics. So when we look at what we call a digital transformation strategy to realize and make Industry 4.0 possible, we're looking at four things. We're looking at four pillars of that strategy. We're looking at, first and foremost, the technology selection. Okay, what technology do you need to create those layers or connect those layers? We're looking at analytics, right? We're looking at performance analytics, like measuring metrics. For example, OEE, overall equipment effectiveness of the manufacturing plant. And at the same time, we're looking at advanced analytics or predictive analytics using artificial intelligence and machine learning, which we'll describe to you today. But for the analytics to operate and to add value, there needs to be connectivity to the factory floor. The CNCs, the PLCs, and the sensors need to be networked, need to be connected, and we need to create what we refer to as a data lake. Okay, this data lake has all the pertinent and useful data points that are collected in real time from the assets to drive the analytics and to drive value for the company. And speaking of value, last but not least, and we usually actually start here and we kind of count backwards. What is the business case? What are we trying to achieve? Are we using technology to improve uptime, to reduce scrap, or what is the reason or the business drivers that is driving technology and Industry 4.0 adoption? And it is very important to start with the business case and to have technology drive that versus starting with technology and then looking for the business case. Okay, so keeping this in mind, of course, there's a lot of definitions there around Fourth Industrial Revolution and how it was born and how it evolved. But I'd like to show this simple schematic here, which kind of shows what is the technological or methodology progression over the years and how it led to productivity improvements. Okay, so now we're talking about the Fourth Industrial Revolution. We're talking about digital connected world. In Germany, or Fraunhofer Institute, they actually refer to this as creating cyber physical systems, or CPS. A cyber physical system is using IT infrastructures to mirror what is happening in the real manufacturing operation. So taking those physical assets, your machines, your parts, your people, and modeling them and marrying them in the IT world using connectivity and using analytics. And some refer to that as creating a digital twin that mirrors your true manufacturing environment in the cyber world or in the IT world, okay? So if you don't know this today, we have entered the fourth industrial revolution, and we are progressing and using connectivity and analytics to drive a digital and connected world. However, there are opportunities in the way, obstacles, and there are also challenges, which are opportunities to help us improve the adoption of Industry 4.0 and AI. And this would lead to the conversation on the technology. First and foremost, it is important to understand that companies are running a variety of IT systems, okay? Some business systems are older, some are running MES, some are not running MES. So this legacy and adoption of a variety of ERP systems and MES systems, could be a bottleneck to the adoption and improvement around Industry 4.0. There is a general need to standardize and harmonize those IT systems so that industry today can adopt newer and more advanced solutions like AI and machine learning. Second, connectivity is key. And some say, that data is the new oil that drives business, okay? But the issue becomes there's a lot of equipment on the factory floor. There's a variety of control types and PLCs. Some are new, some are older. Some equipment is truly decades old. We refer to that as legacy equipment. It's non-Ethernet based equipment. So there is a need to automate this equipment, to use hardware, of some sort, to hardwire to this equipment or to add sensors to that equipment, which would drive cost, right? So it's very important to audit the manufacturing floor and to understand how can we receive data in an affordable and efficient manner from legacy equipment on the factory floor. There comes workforce. I mean, at the end of the day, it's all about people, process, and technology that drives Industry 4.0, right? People, process, and technology. So when it comes to people, we're looking at the workforce. There is change management, and there is culture, and there are people-related things and new skill sets required to use this information. For example, some will ask, hey, do I need to hire data scientists in my workforce in order to be able to do AI, right? And that's a new skill set of a data scientist or a data engineer, some refer to them. And, some of them may not be affordable to some companies, right? So it's important to understand what skill sets are required to help you achieve those new generations of technologies. Then comes new processes, right? How humans interact with those solutions. We refer to that sometimes as HMIs, human-machine interfaces, right? So now that you have new processes and new predictive capability, how can the maintenance organization, for example, interact with a predictive maintenance system, right? How do they trust in the predictions that those solutions are bringing them? So there comes new processes and new ways to use the technology and make the technology an integral part of the manufacturing operation. And last but not least, funding. And I can convert that word into maybe the opposite of that word. So what is your ROI? What is your return on investment from adopting these types of solutions? And I'd like to demonstrate that with a simple slide, actually, okay? It is very important to define your metrics. So OEE, overall equipment effectiveness, is one of those key metrics that is used to measure manufacturing efficiency, right? OEE is availability, which is the uptime, multiplied by your performance, which is the speed of the operation, multiplied by quality, which is your scrap rates. So by looking at OEE and improving uptime, that's a key business case behind predictive analytics, right? If I'm moving from a fail and fix and a reactive type of mode of maintaining my machines to a predictive and preventive and proactive approach to maintaining my machines, this hence will improve the uptime in the facility because you can predict issues early, right? But in addition to reducing unplanned downtime, there is also an interesting link to the maintenance activities, right? So many companies today, they use spare part systems or preventive maintenance systems like SAP PM or IBM Maximo or many commercial solutions out there today. But the trick becomes, how can you bring those predictive insights and use them to leverage and optimize your spare part inventory. How can you order a new spare part just in time to fix your machine and at the same time reduce the spare part inventory on the factory floor? This is actually a key use case, and a lot of manufacturers out there today who are more reactive, they have large amounts of spare part on hand, and that is an overhead and a cost to their business, right? So how can we use predictive analytics to drive that? And at the same time, how can we optimize preventive maintenance cycles by using predictive insights? If I know that my axis on my robotic is going to fail in the next 2 weeks, how can I optimize my PM? How can I assign maintenance labor to do the fixing, right? And I have customers, we have, opportunities and case studies where folks are removing completely maintenance activities over the weekend, right? The reason you have weekend maintenance is you're fighting fires and you're not optimizing your PM. But if you have a heads up, you're able to optimize those activities and improve maintenance activities. And the numbers you see here are true numbers from industry today of clients and case studies who used AI and predictive analytics to drive improvements on those metrics. 5 to 10% OEE gains, 5% uptime gains, 20%, or even I've seen up to 40, 50% reduction in spare parts inventory. That is huge. Reducing PM time, eliminating overhead weekend maintenance, which can be a significant overtime burden to customers today, right? So define your use case and define your business case and use the technology and analytics that we'll show you today to drive these numbers here and to track them. And this is a simple example just to give you an illustration. And those numbers may not apply to your specific industry, but if you look at an automotive OEM who is trying to mitigate unplanned downtime, 500 robots, 1 minute of downtime is almost $10,000 in an automotive OEM facility because you're not making cars, right? Robotics don't fail very often, but when they do, they cost 30 minutes of unplanned downtime, significant cost. And by using predictive analytics and just capturing a fraction of that prediction, only 50%, only 1 in every 2 failures are caught by the predictive system, which is an under-promise, actually. Typically, predictive systems can help you achieve 80 to 90% prediction accuracies in some cases. But the annual savings can be extraordinary. This can drive significant improvements. And here, we're just looking at uptime. We are not considering the ROI of spare part reduction and PM optimization, right? So to conclude the setting the stage here, it's important to select the right solution for your business, but please understand that any solution has an input and an output. It's like an engineering function, right? Input, process, output. The input is your data lake. And we're going to show case studies around what data do I need to capture? What data does it come from the CNC, the PLC, the sensor, the quality information that may be collected on the machine or inspection equipment? And then how do you crunch that data in a systematic way? And then how do you deliver predictive use cases around the machine itself, which is focusing on maintenance, and around the part that is being produced on the machine, which is focusing on prediction of scrap and reduction of scrap on the factory floor. So take the data lake, define it, and collect the right data that makes sense. Deliver it into the industrial AI solution templates, which can help you drive data collection and analytics for the robotics and casting and other equipment in your manufacturing plant. And then define the use case that can drive your business case of improving uptime, improving spare parts, and reduction of scrap. So this is the cornerstone of what my colleague, Dr. Siegel, is going to chat with you about. And he's going to give truly practical case studies of how you can do this today in industry. So with this, David, feel free to go. Thank you.
Thank you, Mo, for the introduction and setting the stage. So I would like to share the technology as well as various use cases on how it can bring value to industry. Before talking about the case studies, it's important to talk about the challenges and key questions that people are. The first main question is the business case that Mo was talking to. and selecting the right use case for the given manufacturer that will provide the most bang for your buck and the most value. And once you start along that path, you then have to ask what data is available, the connectivity, how do I collect the right data at the right quality, at the right sampling rate to eventually make the right decisions. In order to make the right decisions, you need to have the right analytics, the right analysis tools to make sense of all that data that you're collecting from the various machines and processes. And then from there, you then have to decide, how do I present this useful information to my end users, whether they be maintenance technicians, process engineers, maintenance managers, whoever is going to digest this information and then take the appropriate actions to make the right decisions and ultimately improve the productivity of that facility. So we've heard a lot about AI, machine learning, IoT technologies, and we've reviewed some of the published reports on these technologies. And there's actually been reports that some of the pilots have not been successful, and we've kind of looked at some of the underlying reasons. One is that perhaps the business case wasn't clear, the ROI wasn't well defined, or maybe the people working on the project were doing too much development effort versus having a more out-of-the-box solution. So we want to take that previous state and move to a future state where we're looking at a clear business, a software that is mostly out of the box with pre-configured templates that allows us to have more rapid deployment of this technology and ultimately greater industry adoption. So in order to have a platform that can have the right functionality and features, we've kind of looked at three key aspects. One is collecting the right data at the right time and the right quality. That includes the ability to synchronize data from different data sources, for example, sensory data that you may add to the machine, or existing data maybe from the PLC or other control systems. In addition, you may need to incorporate data from other data lakes, whether it be quality data or data about the production operation. So that's kind of an important element of how to collect the right data for eventually delivering the value that you're looking for these initiatives. The second part is, how do you analyze all this data? And what we found from our experience, it's not that data comes in, there's a secret or magic algorithm that does everything and analyzes all the data and outcomes and results. It's more of a step-by-step approach. We call it a template-based approach, where data comes in, you clean the data, you kind of scrub it, remove outliers. You then maybe organize it or segment the data on a cycle-by-cycle basis. If you look at a lot of manufacturing equipment, they're mostly operating on this kind of cycle-by-cycle operation. For example, they're making different parts, and they have different cycle times and operation along that theme. So once we kind of segment the data in that manner, we then extract features or patterns from that data. And then we apply the machine learning after we've gotten to that third step. And then we eventually settle on the analysis flowchart or template for that given equipment or processes. And once that's configured, we also then deploy the results using various software and techniques. So eventually the end user can digest this information and know what action is needed as the machines and processes are developing potential issues. So these are some examples of our solution templates that we've seen in manufacturing. For example, predictive maintenance is a very popular theme. We've seen various use cases on industrial robot predictive monitoring, also for CNC machine tools and stamping. Another popular theme that we'll also highlight is the notion of predictive quality, where the focus is on scrap reduction. So it ultimately goes down to reducing maintenance costs, which is a theme for predictive maintenance, or improving quality or reducing scrap, which is a theme for predictive quality, and all goes back to that performance metric of OEE, which is again based on performance, quality, and availability. So let's look at some additional aspects of the analytics. So you'll notice that there's a variety of different techniques listed on this slide, and it kind of highlights the notion that one size does not fit all. Different techniques, different analysis methods may be more suited for a given type of data or equipment. And we found that finding that sweet spot of which technique works the best for a given equipment is part of that template-based approach, and allows us to have higher accuracy, which ultimately leads to better decisions and better adoption of this technology. And then at the end of the day, someone's going to have to make a decision on this information. And what we found is it's great to kind of reduce all this data into what we call a health index. It's a value between 0 and 1 that tells you if the machine is healthy, or kind of a warning level, or if it's getting to a red level. So again, this is a kind of a simplified way of presenting the information to a maintenance technician or a process engineer, and allows them to have an easy to understand dashboard to take the appropriate action and make the right decision. So with that overview in the AI technology, let's go a little bit deeper into various case studies. So the first one is on predictive maintenance of industrial robots. And for a lot of equipment, not all of the failure modes are potentially able to predict. They don't necessarily have an early symptom or sign that they're going bad. So you can kind of divide the failure modes for robotics into these two categories. The preventive maintenance, or PM, that Mo was referring to, are maintenance or failure modes that are best served by doing routine or preventive maintenance. For example, in your car that you may own, you may change your oil after so many miles. Same thing with the industrial robot. You may want to inspect the cable or provide lubrication to address those potential preventive maintenance failure modes. For the other failure modes that are more predictable, you can use data that you're collecting from the robot to find these early symptoms and use that to find potential precursors to failure, and then use that to predict when a failure may occur. So with that in mind, we'll go into a little bit deeper into the solution template for industrial robots. And these were the 4 requirements. One is that the dashboard has to be easy to use and understandable, because if it's not, you'll have a less chance of people adopting it on the shop floor. The second part is that it should be based on data, data-driven. The requirement is that it should use existing data from the robot. That will allow it to be a cheaper way of implementing the technology and a faster way as well. And in this case, we're using existing data that's already in the robot controller, such as the torque or angular measurement. And then also, again, it will rely on advanced predictive algorithms based on machine learning technology. So here's an example from a previous case study that we had done for an automotive customer, and showing the health of one of the robots that was actually developing a problem. You'll notice that the health value is getting close to that warning limit, and our prediction is saying that in the next month or so, it will reach a very severe state. So the customer used this information to take action on a weekend shift. They were proactive, and they found it. They actually found that it had a problem on one of the axes, axis 5. The software is also showing not only is there a problem developing, our software is also telling you where to go look. It's also saying that axis 5 is the main contributor to this abnormal health condition. So that was a very successful use case on how to apply it to an automotive factory with a lot of industrial robots. The second case study is with a flow-forming machine. This is also another automotive manufacturing example. They're making various components for automotive components. And this is an example of the implementation framework. These are very legacy machines. So these were machines that were over 50 years old. And we had to add additional instrumentation to the machines to make them an intelligent machine and make them suitable for understanding the health of those machines and driving that predictive maintenance solution and use case. So we added vibration, pressure, temperature, position, and RPM and other signals to that machine. And we used various software to collect the data. And then we followed that same template-based approach for configuring the analysis routine and deploying that solution to this particular customer. This is an example of some of the data that we're collecting for the flow-forming machine and some plots of that data. So we're looking at the vibration. And the one thing you can kind of notice on the chart on the right is that it really has a cyclic type of pattern, because it's kind of making this part every 10 or 20 seconds. And if you capture that cyclic data and look at that changes from cycle to cycle in comparison to kind of the baseline condition of that machine, you can train these algorithms and techniques based on machine learning to find departures from that normal behavior. And we've applied it quite successfully in this case study. The first example is for an issue with a chip finish rule. It's a certain part of the machine, and our health index is showing that it was abnormal, as well as trending further and further as that issue was developed. That allowed them information to take action before it got to a more severe condition. A second example is actually a good relationship between the correlation between predictive maintenance problems that also lead to quality issues as well. This was another issue with a similar machine, and it also started developing an anomaly, maybe anomalous condition 10 days prior to when they actually took maintenance action. And this particular template and solution was saying you have this anomalous condition 5 days prior to they actually started noticing quality issues, which is also 5 days before the actual issue became so severe they decided to take maintenance action. So this example is showing that an early precursor can help you prevent these problems from developing and ultimately not wait until a costly failure occurs. Or quality issues may also occur even before the failure. So another example on the predictive maintenance theme is on stamping presses. And this is also a good example because it also highlights the importance of cleansing the data. So you'll see some of those aspects in this particular case study. So for the press machine example, it also was with an automotive OEM. So they're a maker of vehicles and was for their factory and shop floor. And they also wanted to develop this predictive maintenance solution for their press machines. They were very critical. Fortunately, they had collected maintenance records from their maintenance management system, so we had an idea of the potential problems that had occurred in the past. They also had collected historical data, which we could use to kind of develop and validate the predictive maintenance model. So if at a high level, the flow chart or high-level view of this application is that we're collecting various data from the press machine. In this case, it also did not require any additional instrumentation. All the relevant data we could collect from the PLC, including temperatures, hydraulic pressure, position information, and so on. And from there, we would apply looking at multiple parameters, what we call multivariate analysis. And another important element is that data cleansing aspect to have appropriate, clean data to work with to identify abnormal patterns in the data, and then ultimately convert that into a health index that the user can digest and make the right action for. So with the maintenance records, we reviewed them, and some were very short term, but we decided to focus on the more long-term maintenance events, the ones that cause longer downtime. And in summary, they were really focused on abnormal locking events related to the hydraulic system. That was the focus of the predictive maintenance use case for this example. And before we could apply the machine learning, you'll notice on this chart on the left, there's a lot of these outlier points that don't conform to the typical cyclic pattern in the data. But if you perform that pre-processing, you end up with a much cleaner and more representative pattern that you can then analyze and feed into the machine learning algorithms and techniques. And we did that quite successfully. This is based on historical data to prove out that the solution worked and provide evidence to move forward after the pilot phase. So you'll notice that initially the machine was really healthy and started developing this problem several weeks in advance before the hydraulic failure occurred. So with this solution in place, they could have predicted and prevented this failure. And again, it showed the evidence that based on the historical data, the solution would have provided value. So the last example I want to highlight is focus on the theme of predictive quality. And this is also a very popular theme that's received I would say increased level of interest the last 2 years. And this example is focused on a high-pressure casting process. And in this process, they're collecting a variety of different data, pressures, temperatures, cycle time information, a variety of different signals are being collected. And they first want to kind of visualize the data, get a feel for what's going on, kind of understand where they are at currently in the process. And we provided these types of dashboards so they could easily digest this information in an easy-to-understand manner. In addition, for some of the more interesting signals that are more related to quality issues, whether they're related to porosity or other issues in the casting process, we apply more of a sophisticated analysis, based on pattern recognition. We call it kind of curve-based analysis, where for each cycle there's these pressure and temperature curves, and if you look at the subtle differences in those curves, you can then find the indicators of potential quality issues and detect it at an early stage, then you can prevent the cost associated with detecting it at later stage in the manufacturing process. For example, in the machining steps. So that's where the real business driver is for this use case: the early stage detection of quality issues versus the later stage where it's more costly for them. So I think with that in mind, I'll pass the ball to Mo, who will talk about the ROI associated with this technology.
Thank you, David. Thank you very much. And I think it was good to witness some of the real case studies of applying AI technology in robotics, stamping, casting, and again, going back to understanding the use case. Some of them were focusing around the machine itself, predictive maintenance, while others were correlating the machine data with quality data and then offering predictive quality insights, right? So there comes the question of where do I start and how do I create a strategy to gain ROI with AI investments? So I'd like to clarify that and show you a high-level phase approach on how you can today improve your digital transformation journey, or how you can start your digital transformation journey, depending where you are in your strategy. And then would like to wrap it up and get questions from the audience. So let's start here. So it is important to find your proof of value. And we always find that it's good to think big and to think about putting predictive analytics in all my factories. And I have 25 plants globally on 4 continents. So, I mean, thinking big is good. It's good to have a high-level picture of what you want to achieve. However, it's strongly advised and recommended that you think big but start small, okay? You select one plant, you select several assets in that plant, and obviously select the right factory and the right machines to start your proof of value, and then prove that value. And we refer to it as a proof of value because a lot of the techniques and technologies that David went through with you today, they are not new by any means. Those technologies are available. There's a lot of solutions out there that you can explore and investigate and bring into your company today. And it's important then not to deploy proof of concepts, but to deploy proof of values that deploy proven technology with a business case attributed to that technology. And once you prove that, and this is what we refer to as templates, solution templates, you can scale fast, okay? So let's discuss how we do that. We have a 3-step approach that we follow with customers. We refer to it as a 3D approach. We discover, design, and deliver. And this is a generic approach that anyone can actually follow to deploy such solutions in your environment. And it all starts with an assessment. It starts with a discovery and a selection of a specific facility. It starts with understanding what is your digital maturity around 3 key areas: your people, your process, and your technology. Once this assessment is understood, and in some cases training has to be provided, or similar to the training we're giving today, it's then important to go into a series of workshops around what is your baseline. It's important to understand where you are today, which will then lead you to the future. So reviewing your current systems, your processes, your technologies, selecting several workplaces and a data collection strategy around those use cases. David mentioned, hey, some case studies had very old machines. We had to put sensors, while other case studies were highly automated and all the data was coming out of my casting machine, for example, right out of the controller, right? So it's important to understand that maturity level and to create a data collection strategy around it. And last but not least, what is your business case? We talked about improvement in uptime and reduction in scrap and optimizing spare parts, right? So document that business case, because that'll be a key metric that you will track during the next step, which is your proof of value, okay? So once you have your gap analysis in place and a statement of work is delivered, which clearly outlines your hardware and software and service needs that you need to do for this proof of value, start your delivery and implementation process, right? And continuously communicate and track your findings, deploy it technically, deliver the training you need for the key users, the maintenance organization, the quality organization, and we sometimes talk about creating a center of excellence environment, which I'll talk about in the next step. And last but not least, track and achieve your ROI. And those proof of values should not typically run more than 3 to 6 months. If you're seeing that your proof of values are going beyond that time frame, do an investigation, do a lessons learned, and understand what is the reason. Is it, again, around people or process or technology? And pivot into maybe a new plant or a new process or a different machine. So understand, why is my proof of value taking longer than expected, and why am I not meeting my success criteria, and decide when you should pivot into a different domain and deploy or maybe restart the proof of value. Last but not least, scale. Okay, we have seen many industrial clients who actually create their own internal center of excellence, and over time they start staffing data engineers, data scientists, connectivity people, and you can actually train the center of excellence within the company, which is typically a multidisciplinary team from IT and from OT, to take ownership of the templates and ownership of the proof of value and many of these AI case studies that David showed today, and be able to scale them almost autonomously across a large enterprise of multiple manufacturing plants around the world, right? So the scale phase becomes key, but only once a proof of value has really shown that the technology works and the business case works. So discover, design, and deliver. Think big, start small, and find your proof of value, and act now to be more competitive in the market space. So last but not least, if you have not started your digital transformation journey today, start. And if you have started, think about what you can improve in your digital journey. Continue thinking big and starting small. Start creating that center of excellence environment in your manufacturing facility and in your corporate organization. Make your strategy operational. Act now with a proof of value that has very clear business success criteria to it and a very clear definition, statement of work of what is the technology that you are deploying. Whether you're making parts in a factory or whether you're sensorizing your own products, and we have not talked about this today. We have many clients that are offering new business models, subscription-based models to some of their clients who are sensorizing their products and using some of the analytics that David shown today to embed it in the next generation of their stamping press or next generation of their pumps or next generation of their robotics or casting machines, right? So smart connected products are still using some of those analytics to also drive new business models. But in the manufacturing space, smart connected factories are all about a zero downtime and a zero defect vision, using predictive maintenance and using predictive quality to achieve that vision. But to achieve that vision in true and practical setting, organizations today need to find the right place to start, and they need to understand that your weakest link, whether it's people, process, or technology, will impact the benefits you accrue. So it is very wise in your strategy to find that plant to be your showcase or lighthouse operation for AI and predictive analytics, and keeping in mind the maturity of the people and process and technology within that manufacturing operation. So with this, I would like to thank Dr. Siegel, CFE Media, Kevin, and the team. The following is our contact information, and I'll hand it back to Kevin for Q&A. Thank you.
Well, thanks so much, Mo. Don't go away. I'm sure we'll have some questions for you. And to our audience, type your questions in the Ask a Question box on the screen. We'll get to as many as possible in the time allows. Questions that we don't get to the answers will be posted online with the archived version of the webcast. The first questions I'd like to address is a couple of people asked about a couple of acronyms, and that's MES, which is Manufacturing Execution System, and ERP, which is Enterprise Resources Planning. MES is kind of the operations system that sits in between SCADA and the enterprise system and is primarily concerned with things like scheduling or work instructions. ERP, enterprise resources planning, of course, are the large enterprise systems, the single source of information that's used to run most manufacturing enterprises today. In fact, two of our sponsors today, Epicor and Oracle NetSuite, are providers of enterprise resources planning. So that's that. I guess my first question for you, Mo, is who's more important in these kinds of engagements, the subject matter expert or the data scientist?
It's a good question, Kevin. I mean, we believe in a multidisciplinary team. So there are some folks from the IT side and some folks from the OT side who would be part of these assessments. And I think there is a hand-holding that happens between the data scientist and a subject matter expert, because some of these analytics will be best configured by getting some additional insights from the experts and using them to improve the models. So even though the models are pre-built, but getting additional expert knowledge will truly improve the time to deploy, and the prediction accuracies of some of these models.
Good. And let me ask you another question that I often wonder about. I think when someone tells me they're doing machine learning, I kind of understand what that is. It's pattern recognition historically and comparing that to present operation, et cetera. But artificial intelligence seems a lot more ambiguous to me. Do you think that that's primarily a marketing term, or are there actual techniques that you think are used today in manufacturing that are expressions of artificial intelligence technology?
I mean, there absolutely are techniques, and I'd love if Dr. Siegel, chimes in on this. So, David, do you see definitions of AI, and what are your thoughts on that?
Right. So, from my perspective, artificial intelligence is kind of the umbrella term, and under that term is machine learning. So, pattern recognition is a form of machine learning, as well as various regression and classification and clustering algorithms. But you're right. I think the level of artificial intelligence applied now is good, but it's not necessarily a level of reasoning or things that are more advanced, that are some of the articles that are talking about the future state of AI and things of that nature. So I think there's still ways to go in the technology reaching that level. I don't know if it would ever reach the level of human reasoning, but I think there's more to go beyond the techniques that are being applied today. But I would still consider machine learning as a form of AI technology, and the examples that we showed here were based on machine learning methods and models.
Good, thanks. Another interesting point someone's asking about is if they have experience, they have experience with supervisory control and data acquisition. If there's somebody you can refer to as a SCADA guy, and I do know some people that I would describe as being SCADA guys. Some of them are really very highly technical, qualified. The question that's being asked is, where should a SCADA guy, where should he start to get information about digitalization? What areas does he need to go to kind of up his game in this new era where IIoT is having, and information technology is having such a huge influence on operations technology? David, I'll address that to you first, if you don't mind.
Yeah, that's an excellent question. So I think SCADA systems are that data layer that Mo was referring to on the pieces of the puzzle to that Industry 4.0 initiative. And there's a lot of places to start on that level, and as well as reading about literature of what is that next level after you've collected the right data. And it really goes into some of the techniques we talked about of how to analyze that data, how to make sense of it, and how to ultimately provide value to your organization. So the SCADA people are a really important piece to the puzzle from my perspective. Maybe Mo has more to add on where they fit into this overall scheme of things.
Yeah, I absolutely agree with David. They're a key piece of the puzzle, and organizations who have SCADA systems today tend to be more mature and have the readiness of the data and the richness of the data available. I just want to say that predictive analytics solutions are extremely complementary and they add value to existing SCADA systems. And if you're running a Schneider or an Ignition or a Kepware or you name it, there's so many out there, you know, predictive analytics solutions, just like MES, can tap into SCADA layers and can use the data and apply AI and machine learning and pattern recognition techniques to deliver more insights and more value from the data versus the SCADA systems, which are typically focused around just monitoring, trending, and potentially some alerts. You know, if things go up or under the spec, you know, predictive analytics can offer a true multivariate approach and a learning approach from those SCADA data sets. So we see them as extremely complementary to each other.
Great. Next question. One of our listeners is asking about how important is data pre-processing and how can that be standardized? I mean, it is interesting to think about. Is the data quality sometimes so bad that it's not capable of delivering value, or are there just simple steps that anybody could go through in order to make that data more meaningful? I'll address that to you first, Mo.
I'm just going to respond with 4 words: garbage in, garbage out. And David, if you can talk about data cleansing, I think that's a key point of the whole analytics framework.
Right. I think data cleansing can help, you know, above average to good data to be really good data for the modeling purpose. And there are some standardized approaches that we found for different types of equipment and sensors. For example, there's data quality checks that you can perform on vibration data. You know, there's outlier removal techniques, and we found it very important because ultimately you want to drive down that false alarm rate so people will trust your system. And if you don't do any pre-processing, the likelihood that you'll have more false alarms is much higher. But I agree with Mo. It can salvage, you know, average and maybe above average data, but if your data is really poor, you have to go back to that data layer and address those issues, you know, right up front, because you'll just be, you know, spending so much time and energy and ultimately probably not getting to the right solution at that point.
Good. David, let me ask you a question about methods or algorithms behind prediction. We talk about statistical methods. We talk about machine learning. There's often discussions about neural networks. Are there some basic conceptual differences or distinctions that you would make there in trying to communicate the significance to our listeners?
Yes, I think, you know, of course you can break down the different methods in different categories. For me, it's more based on scenario, what you have and what you're trying to achieve. So for me, if I'm looking at predictive maintenance, a lot of our algorithms that we've used in our previous case studies are what we call baseline-based methods. They're using data from just the normal condition to understand what normal is. Now, they could be a type of neural network, they could be a statistical method, a regression algorithm, what have you, but they're all based on that concept. And if you have a lot of past failures, you can start not only learning what normal is, but what those failure signatures are. So I kind of view it more on that scenario-based approach. And once you understand what scenario you're in, then you can look up what methods may be applicable. And of course, if you have past experience, you can also leverage that as well to have a better understanding of which method will likely work the best under this scenario.
Great. Thanks, David, and thanks for joining us today. Mo, the final question today is for you. And a lot of the people who follow Plant Engineering Magazine are very interested in motors and drives. And one of them is asking, what are the data points or data types that are ideal for predicting the performance of AC motors and drives?
Well, that's a very good question. So within our template library or library of templates, we do have predictive analytics templates for motors and drives. And there's actually an annual consortium where we do go and present the case study in more detail. But on a very high level for motors, we're looking at electric current, you know, amperage, for example, of the motor. That is a key signal. In some cases, we use vibration sensors, add-on sensors to mount it near the motor, and this might be able to capture issues with the chain or sprocket of the motor itself. So we've done, you know, clients that are using conveyor systems, and the conveyor systems are controlled by motors, and there are chain breakages and roller failures and things of that sort. So I would say primarily electric current data and in some cases we add vibration sensors to the asset. And again, if there is interest in more, I mean, we have complete documentation and presentations around the motors that we can share maybe as part of the follow-up to this webinar.
Great. We had a great number of questions that came in the final minutes. And as I mentioned before, we'll try to answer as many of those as possible along with the archived version of the webinar. But that's all the time we have questions for today. Thank you for the questions, and we want to thank our speakers, David and Mo, for sharing their time and expertise. I'd also like to extend special thanks to our sponsors, Epicor, Oracle NetSuite, and Wago, for sponsoring today's event. And now that we're just about done, we'd like to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it because we use this information to improve our webcasts. Finally, on behalf of Plant Engineering and CFE Media and Technology, I'd like to thank you all for attending. This includes our webcast, and we look forward to seeing you next time. Have a good day.